Good morning, everyone. Welcome to our webinar on gold nanoparticles. There'll be two presenters today, myself and Chris Jones. Chris Jones has worked at BBI for about 13 years. He's been employed at BBI as our gold nanoparticle production managers. So he spent his time making these particles, and he's lastly moved over to the technical support team. Myself, I'm Nikki Robinson. I've worked at BBI for 25 years, overseeing the production of the gold nanoparticles and also working on the conjugation, primarily of antibodies to those gold nanoparticles. And in the last year, I've also moved over to technical support. So we're going to start with Chris, and he's going to take you through the surface chemistry of our gold nanoparticles.
Thank you, Nikki. So as Nikki mentioned, I'm Chris Jones, and I'm going to take you briefly through gold nanoparticle interfacial structure, and we'll talk about a few of the other properties that affect its ability to be used in conjugation. So there you go. So you can just see briefly what myself and Nikki look like. And then we come to my first slide, which is a simplified view of gold nanoparticle and its surface structure. So one of the reasons that gold nanoparticles are suitable for use in lateral flow devices is that we have very high surface area available for conjugation. So 1 litre of BBI's standard concentration, 40 nanometer copper colloid, the surface area of over 2 square meters. When we look at the cartoon, we can see here that we've got the simplified view. So we've got a perfectly spherical gold nanoparticle, and then there's a distinct layer, surface coating, which is associated with the gold nanoparticle. And this is a layer that looks to be of consistent thickness around the particle and of concentration as well. But that's not really the entire picture. So we're going to go into a little bit more detail of the gold nanoparticle interfacial structure. So this slide is a high resolution transmission electron micrograph of some gold nanoparticles. And the first difference we can see between this image and the cartoon on the previous slide is that the particles aren't true spheres. We can see facets in the gold nanoparticles, and this can be seen as areas of darker shading on the particles compared to lighter areas, and this shows the facets on the particles. So the particles are formed by the citrate reduction of a gold chloride solution, and this means that the gold nanoparticles nucleate out solution and they grow as a crystal. So rather than growing as a true sphere, we have a crystalline structure, and this means we can see the facets on the nanoparticles. So it's important to remember that the particles, although they're referred to as being spherical, they are actually, we should really use the term, they are amorphous in structure or isotropic with regards to particle shape. But because they grow as crystals, they're not going to be a true sphere. They will have these facets to them. So we've got another cartoon now which contains a little bit more detail on the interfacial structure of the particles and what we've got actually happening on here. So in this cartoon, we can see that our gold nanoparticle has a negative charge, and then due to that negative charge of the particle surface, we've then got positively charged ions which are absorbed to the gold surface. And this is known as the Stern layer. You can look at the Stern layer of the particles, and you can treat the system as being like the planes of an electrode. We've got an electrode which is immersed in an electrolyte, and that is where the initial modeling of the surface charge was first done. If we look into a little bit more detail on the cartoon, we can see that after we've got the layer of the positively charged adsorbed ions, there's then a layer of counter ions, and we then have these alternating layers of counter ions as we go out towards the bulk solution away from the nanoparticle. So there'll be a layer of positively charged ions, then a layer of the negatively charged counter ions, another layer of positively charged ions, and so on, the concentration of which gets less and more diffuse as we move out into the bulk solution. At a certain point, as the particle moves through the solution, there'll be a distance from the gold nanoparticle where the ions and counter ions won't be moving in such a way that they're just associated with the gold nanoparticle. And this is referred to as the slip-in plane. The slip-in plane is what we use for the measure of zeta potential. So the difference in charge between the particle surface and what exists at the slip-in plane is referred to as the zeta potential. It's also worth noting that when we analyze the particles by dynamic light scattering, this distance from the center of the gold nanoparticle to the slip-in plane, that is the hydrodynamic radius of the particle, and that is what is used as a description of the measure, the Z average, as reported in the DLS analysis. So in the next diagram, we can see an actual measurement we've made at BBI of the zeta potential of some of our 40 nanometer gold colloid. And from this this diagram, we can see that there is a single peak at around minus 40 millivolts. And this indicates that we've got good particle stability, we've got a good level of charge. The particle stability of the colloid is conferred by this net negative charge of the particles. So in summary, interfacial structure is more complex than it might first appear. It's not just a single homogeneous coating that exists on the particles. We have a double layer of oppositely charged ions which exists at the surface of the gold nanoparticle, and this is referred to as the electric double layer. As particles within the colloid begin to approach each other, repulsive interactions occur when the diffuse layers begin to overlap due to the net negative charge we have. This causes the particles to be able to repel each other and remain in solution. The repulsive interactions form the basis of colloidal stability, and this means that the gold nanoparticle surface is considered to be pristine and ready for the conjugation of proteins. As the only thing providing that stability is these layers of, it's this layer of negative charge around the particles. There's no other stabilizing agents such as PEG or CTAB on the surface, which could interfere with the conjugation of the protein to the gold nanoparticle surface and have to be removed. BBI's gold nanoparticles are considered to be monodisperse in relation to both particle size and to their distribution. So that says that they're not aggregated within the solution. In relation to conjugation, this is a prerequisite for having controlled, consistent signal intensity. So to control the monodispersity regarding particle size, BBI has a specification it applies to the particle size, known as the coefficient of variation or the percentage CV. For the particles to meet this specification, they must consist of a monomodal, monodisperse population of particles with regards to particle size. So to put it in simplistic terms, if you buy a 40 nanometer gold colloid from BBI, you can be assured that you're getting a population of particles around 40 nanometers in diameter and not a mixture of particles of around 20 nanometer and 60 nanometer, for instance. In that case, the mean particle diameter would work out to be 40 nanometer, but the particles would fail the CV specification. So thank you for listening to my talk around interfacial structure and particle properties. I'm now going to hand you over to Nikki, who's going to talk you through conjugation of proteins to gold nanoparticles.
Thanks, Chris.
Okay, so when we're developing lateral flow assays, most people will head off and look for a 40 nanometer gold particle. And it's interesting to really understand why the world is set on 40 nanometer particles. When we've looked into that, most people tell us it's because the protocols for production are readily available. You can find them on the internet. The Turkovich method of production of gold is well described. It's an easy, facile one-pot synthesis. It can be made in-house at small scale, and the output, what you produce, is good enough. It does produce a strong red signal on a white background, and that's great for yes/no type tests, pregnancy type tests. The other good thing about a 40 nanometer particle is the ratio of the size of the particle when coupled with an IgG antibody. An IgG antibody is about 8 nanometers in size, and so the two of them together work very well. Without the 8 nanometer IgG particle being overshadowed by the 40 nanometer. It doesn't interfere with its activity. But recently, I think we've all seen that developers are really pushing the boundaries on lateral flow, trying to optimize practically every material and pushing for those semi-quantitative or even trying for quantitative assays. There's published research which indicates that you can get an increased signal strength at low antigen conditions by increasing the particle size in gold-based lateral flow tests. And I just want to explore that a little bit and show you some work that we have done looking at this. So we took our gold particles 20, 40, 60 and 80. And as Chris said earlier, we're really clear about making sure that these are very distinct sizes. We took the 20, the 40, the 60 and the 80 and we conjugated them using our standard methodology with the same antibody, which was a monoclonal antibiotin, IgG antibody, and we produced 4 gold conjugates. We put these into a very simple direct lateral flow test with biotinylated rabbits striped down, and we looked at the performance visually and with the CAMAG reader. Now we ran them all at an optical density concentration of 2. Okay, so we're not really there compensating for the number of particles per mil, but we use that as a standard to compare the particle sizes. One thing you should note, if you look at the table on the right, is that when we put had the strips read in the CAMAG, we adjusted the filter to read at 555 nanometers. Okay, so if you look at the graph on the right-hand side now, you'll see the difference in performance between the 20, the 40, the 60 and the 80 nanometer gold conjugates. And if you particularly look at the 0.125 microgram per mil level, you'll see clearly the 20 gives the lowest signal intensity. Then you get the 40. The top signal, the most intense signal, the strongest signal strength comes from the 60 nanometer. And then the signal intensity drops off again using the 80 nanometer gold particle. Visually, we took some pictures of the strip focusing really on the 40, the 60 and the 80 nanometer. These aren't the best pictures in the world. It's really hard to capture this. But if you look at the 60, you can see that on the 4th line down, you can see a stronger signal strength than you can see on the 40 and on the 80 nanometer. Okay. Also, you see a subtle hue change. You see the color change a little bit. So from the 40, we've got that nice cherry red color. On the 60, we're getting a more purple color, but it's very defined and it's very controlled. And then as we move towards the 80, we're getting a slightly browner color, which doesn't really help with visibility on lateral flow strips. Okay. So the advantages of the 60 nanometer are that we can control the particle size to influence signal strength. When we conjugate to a 60 nanometer, you do use slightly less antibody per mil of gold conjugate. So you're going to see a slight saving in antibody costs. You see increased signal strength, which could be a competitive advantage when you're just looking for those tweaks in performance to give you that edge. The 60 nanometer that we make is in stock, it's on the shelf, and it's got a 12-month shelf life. It's ready to use, there's no dilution required, no buffer exchange. We can make it in batches of up to about 64 litres, and we can go larger, but that's our current standard batch size. And you can conjugate it just the same as you do a 40 nanometer. So we looked there at how you could improve signal strength by tuning your particle size. But you can go the other way. You can look to shift the shape of your curve by altering particle size. Now, this is an extreme example. This is a test that we were developing where we were trying to get a curve that would perform between 0.1 and 10 mg per mil. I mean, that's very extreme. Okay. When we used a standard 40 nanometer particle, which is the black triangles on the top of the graph, you can see that the peak plateaued around 0.1 mg per mil in the target area that we wanted to look at, and then it began to drop off. Okay, so we had an idea that we could tune this by decreasing particle size. So this is previous work. We moved to a 15 nanometer, and yes, we did see the shape of our curve starting to change. And when we pushed all the way down to the 5 nanometer particle, again, you can see that's quite a different curve profile just by changing the particle size. Okay, so the discussion really has covered the relationship between signal strength, curve profile, and size of gold nanoparticle. So as you're optimizing every part of your lateral flow, I think it is quite important to assess a range of gold nanoparticles during feasibility and during optimization. Don't just go with the flow, or don't just go with a 40 nanometer just because it's well described. Obviously, we can help you with that. We've got a range of kits on our shelf of a variety of particle sizes, 20, 40, 60 and 80, available 2 different volume packs. And we've also got another kit, which we call the GCI Kit Life, which looks at the smaller particles, 5, 10s and 20s. Okay. So now I want to talk to you about lean supply and why you would use a supplier to make the gold colloid for you. Okay, it's very easy, and a lot of people, when we've talked to them, have said, well, why do you make your gold in-house? It's one of your key raw materials. It is the material that's going to help with the sensitivity of your assay. Why would you make it in-house? And the answer we nearly always get back is because it's cheap. Okay, but is it really cheap? It can be a false economy. If you go for that facile one-pot synthesis, that's great, but can you scale it up in line with your development program? Most of those techniques are not scalable. What you manufacture usually has a range of particle sizes. So going back to what Chris said earlier, those range of particle sizes means that the particles can aggregate together. So you're going to have a short shelf life on that colloid. So you're going to have to probably make it and then conjugate it straight away. And that's going to mess up your scheduling. You're going to end up with your scheduling conflicts. Depending on how you're analysing it, you're likely to have a high failure rate on this colloid, and you'll just make it again. It's cheap, why not? Just do it again. But you could end up with a failure to supply for your conjugation and then for your lateral flow development. You're going to consume labour and materials by repeating the production. And when you get into manufacturing, when you're looking at your standard BOM costs, if you still have these failures, if you haven't addressed them, then you're going to have increased variance on your BOM costs. You're going to find it very difficult to precisely characterize by DLS or spectrophotometer. So you're going to see variation between your batches. Now, when you're trying to look at lateral flow tests and you're looking at that color, you know, the difference between red and purple is quite subtle, but that's quite different in performance, especially if you're trying to use readers. So you're going to see failure in your quantitative or semi-quantitative devices. And that batch-to-batch variation that I've alluded to will show itself in the peak wavelength, which means, depending on how you're using your reader, you may have to re-optimize for each batch of conjugate that you produce. And the end users, if they're looking at visual interpretation, could see a difference in performance. So at BBI, we're out on a journey of continuous improvement, and we are working towards Lean and Six Sigma. And we've realized that our particles can help you on that journey too. You can buy from us. We're a trusted, accredited partner. We've been around for over 30 years now. Our quality regulations were up at ISO 13485 2016. We have gold colloid in stock, which has at least a 12-month shelf life from date of manufacture. Some of the particles have 18 months, I believe. So that means that you can buy our gold colloid for your development, and you can put it on your shelf, and it will perform the same on day 1 as day 6 months, as 10 months later. And it's there ready for you. Whatever you want to do, however you want to develop, however your market's shifting, your colloid is ready to go. We can make bulk volumes to forecast, so it's produced just in time to support your operations, which means your stock turns are maintained and your cash flow is improved. And you're going to be using, by doing that, by taking advantage of that service, you're using our resource of a dedicated colloid manufacture team. They don't do anything else, they just make colloid. And our scale is already proven, so we can produce the colloid at you can buy it at 100 mils and it will perform exactly the same as a 10-litre batch. Chris, in his presentation, talked to you about a stringent QC release, because we're looking at these particles under the electron microscope. and we are measuring the particles in that way. So we're physically seeing them and tracking every batch that goes out. Our gold, as Chris said earlier, is supplied just in water. It's easily conjugated by standard passive techniques, so you've got no need for linkers or complex covalent chemistries, and you don't need to do any buffer exchange prior to conjugation. It's ready to go. We in-house conjugate of scales of up to greater than 20 litres OD10 with a single batch of gold nanoparticles. And to put that into real terms, that means you can make approximately 2 million tests from a single batch of gold colloid. So thank you very much for listening from myself and from Chris. So I guess now we just want to open up the floor and ask you if you have any questions. We're just trying to unmute you all so you can ask questions. Okay, we should be in a good position now. Does anybody have any questions?
You are able to unmute yourself.
Hello, was that a question?
No, so no questions. Any final questions?
Okay, well, thank you all very much for listening. If you do have any questions, please feel free to send them in. Myself and Chris will pick them up and we'll send you a response back.
Thank you for your time today. Thank you.